Dear students, today in this lecture we will talk about the equivalent circuit of a transformer. Previously we have studied the ideal transformers. In this lecture we will study the real transformers. So in the ideal transformer we had supposed that there are no losses in the transformer, but in real transformer there are a number of losses. So the main four losses we include over here in the slide. The first one is the copper losses, which is directly proportional to the current. So the resistive heating losses in the primary and secondary winding of the transformer are referred to the copper losses, and they are directly proportional to the square of the current. Now we come to another loss, which is experienced in the real transformers. That one is eddy current losses. These are the resistive heating losses in the core. Like in copper losses, they were the losses in the windings. These are the losses, heating losses in the core, and are proportional to the square of the voltage. Another loss is hysteresis losses. Hysteresis losses are associated with the rearrangement of the magnetic domains in the core, which changes during each half cycle of the applied voltage, since we are using the AC voltage. Now another losses are leakage flux. There are two kind of leakage flux: phi LP flux, leakage flux in the primary winding, phi LS leakage flux in the secondary winding. So there are fluxes, as we have studied in the previous lecture, the fluxes which escape the core but not pass in both the windings. They pass through one of the windings. These fluxes produce a self-inductance in the primary and secondary coil. So these are also incorporated, these losses are incorporated in finding the equivalent circuit of a real transformer. The exact equivalent circuit model, we will talk about the exact. In first case, where the losses were the copper losses, so these are very simple to model these losses. These losses can be modeled by placing a resistance Rp in the primary and Rs in the secondary winding of the transformer, as you can see in the slide. So previous was the ideal transformer, and now we have included an Rp resistance in the primary side and Rs resistance on the secondary winding to model the copper losses in the transformer, real transformer. Another case, we want to incorporate the leakage fluxes in the equivalent circuit. The leakage flux is basically the flux which leaves one winding but do not pass to the second winding. So these are the leakage fluxes, and in previous lecture we studied, in the case of total flux, one part was the mutual flux and another part was the leakage flux, both at the primary and at the secondary level as well. But now in this case we can see that ELP is basically leakage flux on the primary side, voltage factor which deals with the leakage flux at the primary side. Similarly, the second part shows the voltage which deals with the leakage flux on the secondary side. So in this case, we know the value of leakage flux on the primary side and leakage flux on the secondary side. The values are written in blue color, and after substituting these values in the above equation we get this third equation, and in this equation you can see that now the derivative of the primary current is taken, which is multiplied by np square to rho, and we simplify this np square rho equal to primary inductance represented with Lp over here. In similar case, there would be Ls on the secondary side. So self-inductance of primary coil and self-inductance of secondary coil. So leakage flux can be modeled by primary and secondary inductances, and we include the primary and secondary inductances in this already modeled circuit, and in this circuit now the leakage flux is also incorporated, the effect of the leakage flux is also incorporated. Now we go to the other losses. The third one is eddy current plus hysteresis losses. The core loss current IH plus E is proportional to voltage applied to the core and is in phase with the voltage. So this eddy current plus hysteresis losses can be modeled by a resistance across the primary winding. So in this case we will put a resistance RC parallel across the primary winding, as you can see on the primary side of the winding. The other part is JXM, which is the reactance connected across the winding, and this is showing the magnetization current, which is also proportional to the voltage applied to the core and is lagging the applied voltage by 90°. So now the ideal transformer have been modeled as as a real transformer. The XM and RC represent the excitation effect, so we call this the parallel uh, The parallel model included on the primary side is called excitation effect, and it includes the effect of core loss current and magnetization current. The Xm and Rc are placed inside after Lp and Rp. Because the voltage applied to the core is an input voltage less than the internal voltage drop of the winding. As we have seen in this figure, to analyze practical circuits containing transformer, it is important to convert the entire circuit to a single voltage level. So for this case, you know that we will try to find an equivalent circuit which would have a single voltage level, either a primary side or a secondary side. So we will change the circuit accordingly in the next slides. In this slide, you can see that the actual model is shown on the left hand side, and this is the actual circuit, but this circuit has been uh, transformed according to the as referred to the primary voltage. If we transform this circuit into this circuit, we have used the transformation ratio. As we know that the transformation ratio is A, and it can be it, it can be found the equivalent circuit by z bar can be found by applying a square into z. So in this case we have transformed the model and transformed the impedance by multiplying by a square. So you can see that the in top figure, this is a square into rs and a square into xs. So we have transformed and multiplied the impedance with a square because the transformation ratio was a. But if the transfer model is referred to its secondary voltage, then is referred to secondary, then it would be divided by a square, as in this case, because we are referring to the secondary side. So in this case, if we are referring to the secondary side, the transformation ratio would not be a, it would be 1 over a. So its square would be 1 over a square. So as we multiply 1 over a square, so it would become rp over a square and jxp over a square. So these are two transformer model, and these are referred to primary and secondary voltages. But we know that the excitation branch, this branch which is the excitation branch, this has very small current as compared to the load current which is over here. So small that under normal circumstances it causes a completely negligible voltage drop in rp and xp. So if this has the negligible effect, therefore the excitation branch is moved to the front of the transformer. As you can see, it has been moved in front of the transformer because it has a negligible effect. Similar case has been done on the secondary side, as referred to the secondary side, that the uh, excitation branch has been moved to the front of the transformer because of its negligible effect. But we know that although it has the negligible effect, but it also puts some complexity in the circuit. To remove this complexity, it can also be of it can also be reduced, and it can also be uh, skipped from the circuit to get the simple circuit without that excitation branch, as you can see in this case. So this is on as referred to the primary winding, and the second figure is as referred to the secondary winding. Thank you.